Okay, आज लास्ट क्लास ही है रिकर्जन का फिर तो।
ठीक है।
सो व्हाट्स द नेक्स्ट टॉपिक नाउ?
After recursion,
हाँ,
I think linked list होगा या stack and views होगा।
लिंक लिस्ट होगा। यस यस, लिंक
हाँ,
लिस्ट होगा। ठीक है। Okay, so let me drop a message, guys. Session starts in 2 minutes. It's started. Session has started. Please join. Okay, so ठीक है, I will share the screen till then. The rest will come. Started the recording. Yes, yes.
like one thing, Surendra, like instead of using this online ID, can't we use VS Code?
VS Code. We
Um,
can use VS Code. Like,
I think it will be much better.
okay. So let me install the compiler. Okay,
Yeah,
and then let's continue on that also. Or maybe Eclipse would be good.
yeah,
That
Eclipse or VS Code, anything is fine.
okay, okay. So like just to like being lazy for installing the compiler, so I use the code set.
Okay, okay.
Otherwise, okay. I guess screen is shared, and here we are. Okay, so makes sense. So there are some problems which we'll be discussing. First, the quick sort. What happened last day, and what was the issue? We'll see that. So basically, the issue was the base case was not set properly. I guess some fix were must. Rest, I guess the logic was the what we already discussed that. Maybe we were missing something. So the quick sort says. So the quick sort works something like this. So pick this element, pick 2 over here, okay, and put it to its correct position. So pick 2 and correct it position to its like correct position. So how to do that? Traverse through the array, find all elements which are lesser than 2. So you have the lesser count. So the next, so lesser count plus 1 will be your correct position for that element. So put it there. In case of 2, I guess the position would be the syntax, right? The syntax, because only one element is less, which is only 1. Okay, so one is being not one being sent here, 5 being sent here, and 2 being here. Okay, so 5 now. So 2 going to its correct position is 5, 2, okay, 1, 6, 3, and 7, right? Now the point was, so what's the point? If you see the array is not sorted, like it doesn't seem to be any change, right? But there is a change. The partition function not just swaps the pivot element. You can choose this as pivot or the last element as pivot. So I'm taking starting as pivot, and for starting I have shifted 2 to its correct position, right? One thing I will do at this partition logic is I will traverse through the array before the partition, before the pivot means this 2, and after this my only job will be to pick all elements lesser than 2 to left side, and pick all elements greater than 2 to the right side. And way to do is put a pointer here, put a pointer on this side, compare the elements. If the elements on this side is lesser than 2, an element on this side is greater than 2, then replace it. So obviously 5 is greater than 2, so original position is here and this will come here. So the next part was 1, not 1 is replaced with 5, right? So 5 comes at this position, 6 goes here, 3, it's 3, and 7. So if we check our pivot now, this was the partition, right? So all elements bigger than 2 are this side, all elements lesser than 2 are this side. Okay. Now the next quick sort call was starting, which is 0, pivot minus 1. So this is pivot 1 and 0. So this is the same index, so it will return. No sorting required here. You can see that. And partition plus 1 to n. So partition plus 1 means 5 to n. Yes, sorting is required here, right? Now again, I'm taking zeroth or the starting point, its starting point as the pivot. Now my pivot is 5, okay? Because the starting is not 0, starting is a starting, right? So here its starting is pivot plus 1. So 1 2 comes over here, 5 is, so 5 is now the pivot. Again, the logic is choose, count the lesser element which is less than 5. So only one is there, which is 3. Swap this, swap this one. So 3 comes over here, 6 be here, and 5 be here, and 7 be here. Now my pivot is now, the partition is now 5. Left hand side, all elements should be smaller than 5. Right hand side, all elements should be greater than 5. So 3, 6, and 7. One pointer at 3, one pointer at 7. Choose element which is bigger than 5 in left and smaller than 5 in in the right. Compare it. So if we compare, we see that 3, no issues. Okay, so with 3, do we not have an issue? No, it is. So where were we? Okay, so with this 3 and 7, no issues. Okay, then to 6 and 7, again no issues. Okay, because like this is also greater, so we cannot do something here. Okay, in that case, now our pivot will be something else. So this 5 remains over there. Okay, now my pivot will be minus 1. Okay, so minus 1, and like these two. Okay, and again these two. Okay, so let's check for this one. What happens with 3 5 6 7 or 5 6 3 7? This is something, a special case which we can discuss. So let me bring it up here. Okay, so let's discuss quick sorting in this small array. So what can happen? Now pivot again comes at this point, which is 5 exactly. Okay. Now our goal our goal will be to our goal will be to put 5 at its correct position. Put 5 at its correct position. So correct position means all elements lesser than 5. Count that. So only 3 is lesser than 5. So only one. So one. So this is one, right? So only one element is found. So one, add one, add one. So check this. So this is 6. This is 5. So 6 comes over here, and the first index, which is the correct index for 5, comes over here. 3 limits over here, 7 limits over here. So this is the swapping part of our partition logic. Next is all elements bigger than 5 on the left, all elements greater than 5 on the right. So there is a while loop going on, okay, with 2 pointers. So all elements bigger than pivot I, which is left, all elements lesser than 5 equal to 5 on the right. If this is true, swap them, otherwise do nothing. So element greater than 5 is here, element less than 5 is here. So this is a swapping time. Just swap this. So 3, 5, 6, 7. So this was your pivot. Now this is small array. So pivot minus 1 to start. Nothing remains here. So this will just return. And 6 and 7 is already sorted. So maybe nothing will be happening here. So, okay, so this was the only logic. Just take this part. Okay, and this, let's come here. So this was the thing for quicksort. Okay, so here is the complete code, and yeah, no changes. Nothing. So just some conditions were put. Just I guess is only run and test it. Okay, so okay, anyways. So yeah, so this is 1, 2, 3, 5, 6, and 7. And best thing, this it handles equal elements. let's say 6, and let's put 5 over here. Let's see, we can handle duplicates. Okay, so 1, 2, 3, 5, 5, 6, 6, and 7. Okay, so yep, this is it for quicksort, and both merge and quicksort. Yeah, code you can like get it from. You want this one, like yes, the logic should be clear. Okay, let's move further. So there is something called as Tower of Hanoi. Not that of like code is not that sort of difficult, but yeah, there's uh, logic on it, so we can discuss that part. Okay, so let me connect the pen, then I can discuss. Rest of these functions, I guess, are easy ones. So replace pi, so this is easy. Given a string compute recursively, so you have to replace pi with 3.14. So like making recursive call to the string. So how do we solve it? So every time we make a recursive call, further recursive call, we try to separate that in substrings. Okay, so substrings is the way to do that, right? Okay, so you can just see the solution also. It's not totally so you have so every time every next recursive call I'm just supplying the substring, right? So if I get a pi, I just replace it and I will solve for the next one. If I don't, just I will call the recursion on the next smaller substring. Okay, and rest are the similar ones. Okay, something tower of no use. You can display. Okay, so let's not complete. So is it connected? It's okay. Should be. Why isn't it? Okay, let's disconnect from the. So why is it like? Okay, looks like we need to continue with the mouse outside. Okay, so the Tower of Hanoi says, let's say there are. So let's say that we have three towers which can be used. Now the question here is it says that Tower of Hanoi is a mathematical puzzle where we have three rods and n disk. The objective of the puzzle is to move all disk from source rod to destination rod. Source rod. So there is a source rod which is having some rings, okay, or disk, whatever you can call it, and so we have to move from source to destination using the auxiliary rod. Okay, so here are the rules. So it says that only one disk can be moved at a time. So you can pick just one disk at a time. A disk can be moved only if it is on the top of a rod. So disk can be moved only on the top. So you cannot pick from like anywhere from the between. Okay, so the top disk has to be moved first. Okay, it says that number of disk can be placed. So no disk can be placed on the top of a smaller disk. Okay, says that no disk can be placed on the top of a smaller disk. Means the below ring should be greater than the upper ring. So let's say that we have two rings over here. Okay, part of the drawing. So you have to push this. So let's say that this is the source. This is the okay. So this is network issue, guys. Really sorry. I thought it was the pen issue. So pen is working fine, but it is not working. So this is the auxiliary rod or the helper rod, and this is the destination we have to reach. Okay. Now there is a smaller disk, there is a bigger disk. Only one disk has to be moved at a time. Okay, so only one disk has to be moved at a time, and you can pick only the smaller disk. Okay, so you can pick only the smaller disk first because you have to pick from the top, and a smaller disk always remain on the top. So it cannot be the condition like the smaller disk is picked like after the bigger. Okay, so you cannot. So that's the point. Now this is just one, and let's say this is just two. Okay. So, what should be the idea, guys? How we can move this one and two to this like the destination? Are you guys getting the problem first? Okay. So the problem is moving all the disk from source to destination. The rule is pick one disk at a time. The smaller disk remains on the top. Okay, and only one. Okay, so obviously that only one disk has to be moved. So how can we do? And with the help of this also, we can take the help of this. So how can we do this? Guys, all of you are getting the problem. Okay. Okay. So here is the solution, like what we do basically. So we can pick this first disk, right? So we can pick this first disk. Since it is smaller, I cannot place it here because if I place it here, I cannot place the bigger disk on the smaller. So a smaller disk cannot be placed here. So a smaller disk is moved over here. Okay. Means one is moved over. Next, once so since we do not have the first disk on the top, now we can easily move the second one. So I just pick the second one and put it to the destination. Okay, and finally, from the auxiliary, I can pick one and put it over here. Is the solution clear, guys? What we are doing here?
Yeah.
Okay, so here is the challenge. The challenge is what happens when we have one more disk. Two disks very easy. Just solve. What happens if we have more disks? More disk, I will just increase a single disk, nothing else. So let's say that now it is one, working, guys. So that's why the features are not working properly. So this is one, this is two, this is three. Okay. Now, what's with the solution? Okay. So follow me. Here is one, right? So what we can do? So we can say that pick this one, pick this one. Let's see that we move it at this point. So let's say that we pick a disk one, and we put at this one. Now what we do is we pick this second disk. Okay, so we have moved first disk, right? Now it's time we pick the second disk. So second disk, can I put it over here? Can I put at one?
No.
Correct. So where should I put it?
Destination.
Okay, let's do that. Yes, all of you can try, right? This is not something, so just want the idea. Something kind of brainstorming, right? The second has also been moved. Now here's the trick. So three remains here, one is here, two is here. Is there any way I can move this third disk?
No.
So where did we go wrong? What if this is the first disk and this is the second? Means instead of firstly, so first we move this to there here. So instead moving one to here, move one to destination, right? And move two to auxiliary. Now three is here, two is here, one is here. Do I have any options? So that I can shift this three to destination? Yes,
Move one to auxiliary.
correct, very correct. So move one to auxiliary. So it's already causing trouble, guys. But anyways, so let me get this done. Move one to auxiliary. Okay, so one can be placed here. No issues in that. Now one is here. Okay, three,
And three to destination.
correct, very correct. So three is here now. Okay, this disk empty. Three is here. One and two is here. How can I move this two to D?
You can move one to source, then two to destination.
Very correct. So move one to source and two to destination. Okay. Finally,
One to destination.
correct. Okay. Let's observe the pattern here, guys. So, and you will be surprised to know the thing. You cannot solve this question using for loop. Can we? How many of you know if we can solve this question using for loop? Let's see. Do we have this power of unknown? No. Okay, and no, right? Recursion everyone knows. Tell me. Relative tower of. Okay, let's see that later. The point is, recursion will be used here amazingly. There's amazing use of recursion. If we carefully look at the solution we are seeing here, haven't we moved n minus 1 disk from start to auxiliary and moved the last disk to destination? What we did in our complete process is we picked n minus 1 disk, we put n minus 1 disk to auxiliary, taking auxiliary as destination, and putting the last disk to destination, and finally is like keeping that all n minus 1 disk from auxiliary. Okay, so here is what we did. First, move n minus 1 disk from source to auxiliary. So 1, 2, 3 moved n minus 1. Same thing we did for 2 disk also. Remember, one was here, then 2 moved here, and finally 1 moved here. So isn't it moving n minus 1 disk from S to A, source to auxiliary, moving on this. This is a really headache now. Okay, source to destination. Minus one. Second, move the last disk from source to destination. Okay, and here is the last one. Lastly, what we did, picked all n minus 1 disks to destination. Picked all n minus 1 to auxiliary to destination. Okay. Now the point is, so which is the auxiliary node in this case? First case, auxiliary node is
Destination.
Destination.
correct. Which is the auxiliary node in this case?
Source.
Correct. So solution looks similar to this only. So no like complex logic over there. Just this. So int n equals to 3. Okay. So let's name the function as tower of knowing. Okay. What we have to do is every time we have to what do we have to do? Every time we have to give n the source vertex, the auxiliary vertex, the source auxiliary the destination. Right? Tower of knowing. So here it comes. Static tower of knowing and print character so that we can see the moves of players. So source char char source auxiliary and yes, I guess that's it. Let's make this character. Okay, so if n equals to 0, 0, if there is and no moves will be there. But if there is moves, goes something like Tower of Hanoi, moving n minus one disk from source to auxiliary, auxiliary, destination as auxiliary. Print the move. So which disk is moved? The init disk is moved plus, so init disk is moved from n plus source to destination plus give a space and here goes plus source to destination. Similarly, that's similar to this one. So n minus one disk from source to auxiliary, keep it destination as auxiliary, and finally from all the n minus one disk from auxiliary to auxiliary to. So what's the destination, guys? Next time.
Destination
Okay.
using source.
Okay. So auxiliary to destination, keeping source as auxiliary. Yes. Yes. Okay. So this is isn't it the same thing I just wrote over here? Source to auxiliary and management. The nth test auxiliary to T and also. So this is the same diagram which I'm going to see. Where were we? So we are here. Let's run. Okay. So one from source to destination, two source to auxiliary. Remember, one source to destination, two source to auxiliary, then one destination to auxiliary. Okay. Then third, so third one to source to destination. The first is to move. One to auxiliary to source, two auxiliary to destination. First one auxiliary source to destination. Isn't the like this was the only thing, right?
Yeah, yeah, that's correct.
So you can check for two, three, four, and so on. Okay. Is it clear, guys? Uh,
Yes.
so I don't like it took me 2 days to understand the solution first when I was learning. Give me a minute, guys. हेलो लाइक क्लास क्लास चल रहा है फ़ोन करें जैसे हाँ क्लास ओके सॉरी गाइस okay so okay maybe you can try with different inputs okay but don't try more than three it will just time taking. Okay, so let's do one. So today will be like completing the recursive thing. So we can proceed with the other topics. So probably starting what we are starting. So guys, do you have backtracking in your lectures?
Yeah, we haven't,
Uh, you do
but
have.
it didn't start yet.
Okay, okay. So backtracking is after trees. Or
Yeah, it is after trees.
okay. So should I teach it first? Okay. Anyways, like, no. Let's do that later. So that you guys are sync up with me. And what about oops? Is
Yeah,
it
oops is done. It is done.
okay? Okay, so oops is after recursion only.
Yeah,
Okay. Makes sense. Okay. Anyways, so we not to start linked list. We'll start with oops the next day. Okay. So what we are going to see now is okay. So this is recursion three. Okay. So there are some questions which we can see. This is interesting. Okay. So the point is print permutation. Given an input string, print all possible permutation of the input string. Given an input string, print all possible permutation. Permutation means pattern. CBA is given, and the sample output should be ABC, ACB, BAC, BCA, CAB, CBA, CB, CBE. Let us proceed. Question is very simple. So, given a string, print all its permutations. What's the reset does? So the string str is equals to permutation selects permutations for ABC, ABC, ACB, CAB, A, BAC, CBA, CBA. Okay. So 1, 2, 3, 4, 5, 6. Permutation 6 it is, right? So pick any character and we can put it in, like put it at any place. So NP2 or NC2 represent something like that. Or maybe okay, I guess it should be NP2. So where we have yeah, so it is NP2. So permutation, right? So 3P2, which will give you 6. Okay, so we have six permutations of the same string. Okay, so how to print all the permutations using recursion? What's the idea, guys? So what should be done? So we have to print. Think of the base case. Think of the recursive calls. Think of the parameter. Okay, base case, arguments, number of recursive calls. Okay. So let's see what can be done for this one. So I will try to write. See if I can. So A, B, C. Okay. Now starting with starting with A. So let's say that I just have a single character. So let's say that I have a single. So how many permutations? Let's say for C, only one. Now, what if I include B also? So let's say I include B also. So B and now let's say that I start with B. Okay. I am getting, so I am getting C from the, let's say that recursion has given me. So here is a point. C. Let's say that I will have a, I will say, I will ask a recursion to solve for B and C. Okay, then I will again call recursion on B and C. I will ask recursion give me answer for C. Now recursion returns C to this B. Now B has two positions. Either it gets attached before C, either B gets attached after C. Is it clear, guys? Okay.
Yeah.
Similarly, now this is supplied by recursion to A, return to A. Now A has options. Either go with the first one, so either get attached to before B and C, or gets attached to between B and C, or gets attached to C and at the end, or gets attached to CB, ACB, CAB, or at the last CBA, and 6 is written domain function. Is the approach clear, guys? Guys, are you guys getting the point?
Yeah.
Okay. So get a string and try to fill the current character, like at every place of that string, and forward it. You'll get the solution at the end. Okay. Okay. So what should the code? So we'll say print all curly sense print augmentations. Here is this string str. Okay, that's it. Static void. Since we have to print, nothing to return. So print all permutation. Okay, string str. What should be the base case here?
If the string is empty, you can return empty string.
Very good. So string is empty. Let's do this part. So 0. Return empty string. Okay. But. Hmm. So what am I thinking is, okay, let's see. Let's proceed with the solution that we can do some optimization of that. Okay. Now I will call for the current answer and okay. Okay. So here is the thing which we need to keep in mind. Hmm. We have to print it. We cannot return it, right? So we have to manipulate parameters. What do I mean by that? Let's see. So if we are to return, so we will learn one more thing today. Okay, so one thing is returning in recursion. Okay. So how you can share data between two functions? How do you share data between two functions? Using the return, right?
Yeah.
Is there any other way? It is by passing the parameters, right?
Yeah.
So either you send it at parameter or you return to that function. So there are two ways you can share data between two functions, right? So since I knew that this is void, I cannot get data using return. So I just included an answer string. So answer string I will supply as a parameter. I can print it anywhere I want. So here I go. It means that whenever this length becomes 0, it's my turn to print the answer. Now it's called recursion in. So how do we call recursion? We say that we say that whatever answer I'm going to get, whatever answer I'm going to get, I will fetch the first string and attach to its all position. Whatever answer I am getting, I will attach my current character to all its position. See this. And how can I do that? Okay. How is this going to help us? Let's see. Answer dot length. Okay. I plus plus 0 to answer dot length. For example, let's say that our answer is equals to PC, and we have to traverse and we have to attach A in the answer at every possible position. So it can be A B C, right? B A C, right? And B C A. How can this be achieved? So zeroth position, first position, second position. Three positions will be there after which we can attach. How can I do this? Easy. So we can say something like, okay, so answer string current answer is equals to answer dot substring. So answer dot substring. So where we have to attach at the before the ith position, before the ith position. Okay, so we have to attach from 0 to. I'll just explain this. Okay, I'm going to current character. So the current character will be str dot char at 0 plus answer dot substring I plus or I guess I answer dot. Now I have inserted this character in between. In between means so I 0. So 0 comma 0. So answer substring 0 comma 0 will give me empty string. I will insert a since size is 0. So I0 answer length I0 to answer length will will be the same string BC I0 to answer length, isn't it, guys? For I equals to 0 is the same, right? BC, and we have added this I over here. Okay, so this is what we have. Okay, and okay, just give me a minute, guys. So, guys, are you getting any disturbance or is fine?
That's fine.
Okay, So we have some disturbing elements in the society. Okay. Anyways, let's focus on our goals. Okay. So we have something like this now. So if you see this logic, this is just adding characters in between, at the end, and everywhere. For I equals to answer.len, this will generate an empty string, and this will return the first total string. See, BC complete. You have inserted A over here, and we are good to go. The last thing which is remaining is, what's the thing only remaining here, guys? So what should be here? Print the answer, right? And how is that going to help us? Let's do this. Control C, Control V. Okay, not this Control C, Control V. str dot substring. So str dot substring. So we have decided for character 0. Now it's time for recursion to decide for the rest of the characters. Right? I have coordinates. Okay. Is this clear, guys? This is step. Modified answer. Modified answer. And so we have already decided for the first character. Now it's time you decide for these two characters. So the rest of the characters. Okay? Guys, all of you are getting this, right?
Yeah.
What we did, we say that we say that what we say that I will take care of this recursion, you do this part. I will take care of the recursion, go through this part. Isn't it the same thing saying I will take care of zeroth character, you take care of the substring?
Yeah.
It's the same thing, right?
But I didn't get this current answer one.
Okay, let's see. So current answer, what I'm sending from main is empty string, right?
Yeah.
Empty string. So I have the character A with me. So I will get A attached over here because this has 0 length. So 0, 0, nothing, just A. Empty string, A passed as the correct current answer.
Okay.
Now, next recursive call is with A. Character is B. So I have length 0 and 1. We will do with it. A, comma B, right?
Mhm.
And what C will do is C, B. Okay. Every loop is making a recursive call.
Okay.
So let's see if we have devised the correct answer or not. So we are getting a Malaysian error because length is a function we have to call. Yes. So here goes the length. Here goes the length. C B A B C A B C C B B C B C. Is it clear, guys?
Yeah, it is clear.
So all of you, like, you're getting the point, guys, right? Okay. Anyone who needs, like, should I go give a walkthrough, or you can do one more thing, guys. I have printed all the permutation in the reverse order. We can print in the, like, valid order, like, not. So this is also valid order. So this is CBA ABC. You can try out with. other approach. Okay, so if this is clear to you guys, you can devise a solution, right? This is the point. What I discussed and what I wrote in the solution are two completely different things. If you guys have noticed, here I am returning, okay, but here I printed. So now you have two solutions for the same problem. I haven't coded this one. This is some other thing I have told you guys. This will help you returning the string. Put your thoughts to the solution, okay? And with this, I guess we are done with recursion. It's time we move to hoops so that we get to know JavaScript in detail so that we learn all these things, right? Static, void, import, class, public, okay, arguments, throws, and all those things. Okay. And someone asked me like, sir, why are we learning Java? We are going to finally learn JavaScript. See, the point is, once you get to know a language completely, everything becomes very, very easy for you. Go learn any language. It's more or less the same thing. Okay, just some syntactical differences. Oops logic. JavaScript is object-oriented programming language. If you know oops, how does it make the difference? Okay, guys. So yeah, just mark the attendance and let's proceed. Okay. Let me share the sheet with you guys, and I'll add the column. And here you go. Please don't forget to mark it. Okay. Let's meet in the next week. Okay, guys.